Welcome. The Northwest Regional Library System is thrilled to be able to have a subject matter expert, Dr. Derek Buzasi, present on the James Webb Telescope today as one of the many NASA community events that are taking place across the United States. To provide a quick bio introduction, since 2012, Dr. Derek Buzasi has been the Whitaker Eminent Scholar in Science at the Florida Gulf Coast University. His research interests include almost anything having to do with the stars, so exoplanets that circle many of them as well. And he began his career studying various aspects of solar and stellar activity, including spots, flares, and winds, and has more recently moved on to studying stellar interiors, convection, and rotation. If you have any questions, please add them to the chat box, and I'll manage the questions at the end of the program with the help of Kelsey. The last note is a quick announcement. Through the Northwest Regional Library System, you can place a hold on an Orion Starblast 4.5-inch telescope to check out with your library card for a 3-week period. There are holds on it, but get in line and you can take it home and explore the stars with your family. There's even a constellation guide that comes with that as well. And we also have a variety of astronomy books and DVDs for all ages in the library collection to check out. So without further ado, I'll be switching the program over to Derek, and thank you so much for joining us.
Oh, I'm happy to be here. And that truly is a full service library. If you're checking out telescopes too, that I hope people take advantage of it. So I'm here today to talk to you a little bit about the James Webb Space Telescope. And so I'm basically going to give a little introduction to it and talk a little bit about some of the science that it's going to do. It'll be at a fairly high level, but I mean, by all means, ask questions if you're interested in more, and I'll try to answer them. I can't guarantee to answer questions about every kind of science that Webb does because the range is so broad that I don't think anyone knows enough to do that. So the plan here is kind of to talk to how we got to Webb. So I want to take just a few minutes to talk about the history of how we got here and kind of where Webb fits in the context of other NASA missions, because it's not flying all by itself. And then talk about why we want James Webb, because we have all these other instruments. Why do we need a new one? What is it? It's one of the things that makes Webb different from, say, Hubble, which is typically what people think of when they think of big astronomical observatories in orbit, is that Webb is focused up primarily on infrared light. So I'll talk a little bit about why that is, and then give some science examples of where we're going. So that's the plan. So here's kind of the NASA astrophysics menagerie, right? All of the telescopes that we have in orbit now, this isn't necessarily all of them, but it's many of them. The dates next to them indicate when they were launched or when they're going to be launched. And there's all sorts of color coding and stuff going on here. Don't worry, there won't be a quiz afterwards or anything. But some of these missions are led by NASA. So you can see, for example, Webb over here, or Hubble all the way in the corner, launched back in 1990. And then some of these missions are coming in the near future. And some of these missions are collaborative, like Euclid, which is a European Space Agency mission that NASA participates in, just as the European Space Agency participates in Hubble and in Webb. So each of these, the reason we have all of these is that each fills kind of a different role. So what I'd like to do is just take a couple of minutes and talk about 3 of them, some of which you probably are familiar with and some of which you've probably never heard of, and just to lead into talking about Webb. And the idea here is just to kind of give you a sense of the range of missions of things that NASA does and how Webb kind of fits into this big picture. So I'll start off by talking about TESS, which is the Transiting Exoplanet Survey Satellite. And TESS you may have heard of because it's been in the news lately. Over the last few years, it's been in orbit. And TESS is a mission to go look for exoplanets. In particular, it's looking for exoplanets kind of the size of the Earth or a little bigger than the Earth around stars that are pretty nearby to us. And the way that it does that is that it looks at huge pieces of the sky. So this big stripe here is a piece that TESS observes. It observes this stripe for about a month, and then the spacecraft observes the next stripe for about a month and works its way all the way around to observe the whole northern half of the sky. And then the satellite flips over and does the southern half of the sky. So every 2 years, it observes the entire sky. And what it does is it looks at these nearby stars and if planets are orbiting them and they're lined up just right, then when the planet crosses in front of the star, it's an event called a transit, the star gets a little fainter because the planet blocks some of the light. And so if you're measuring the brightness, you see this dip go down. And by how big the dip is, you can figure out how big the planet is. And by how often it repeats itself, you can figure out how long the planet's year is. And so TESS has this mission to go find planets. Now, I chose TESS for a couple of reasons. One, because I'm involved with the project, so I have a soft spot for it, but also because one of the things that James Webb will do is look at exoplanets, and we'll talk about that a little bit later. But so you can sort of think of TESS as kind of a finder telescope for Webb, because it is finding planets around bright nearby stars, which are great targets for Webb to go and look at. And so the Webb people in particular like to think of TESS as their finder telescope, even though the TESS people have their own point of view on this. Another mission that we fly is the Swift Gamma Ray Telescope, and Swift is observing the most energetic events in the universe. So this is a telescope that doesn't really look at visible light that we see with our eyes, but actually makes images out of gamma rays. And those come typically from gamma ray bursts, which are caused by neutron stars that are colliding with one another. So they're extremely energetic events. It's kind of a cool mission because it has a little optical camera on it, which looks all over the sky. And when it sees the little flash that indicates there's a gamma ray burst, the whole telescope slews around in just a few seconds to go look at it in gamma rays. Both Swift and TESS are small missions, right? If you stood them up, if you stood next to them before they launched, they'd be about as tall as you are. So they're not huge telescopes like Hubble or like James Webb, but they have very specific missions. Another kind of telescope that NASA launches is Hubble, which I would guess everyone listening to this has probably heard of. And Hubble, of course, is large. Hubble is also general purpose. It does lots of different things. It's not intended to do one specific mission, but a whole range of stuff. It's in low Earth orbit, so it's close to the Earth. It's serviceable. We've serviced it a bunch of times. When the shuttle was active, we sent astronauts up to either make repairs or replace instruments that were tired or old with newer instruments. And Hubble observes at optical wavelengths, so the wavelengths that your eye works at, and it also observes in the ultraviolet and in the near infrared, so infrared light, but not too far from optical light. So Hubble is also part of this historical collection of spacecraft known as the Great Observatories. And usually people know Hubble, but they don't necessarily know all the other members of the Great Observatories. And they all work at different wavelengths. So Hubble, as it says on the right there, is visible light and ultraviolet. But we also, if you start all the way on the left, had a spacecraft called Compton, which observed gamma ray radiation. We had Spitzer, which observes infrared light. We'll see Spitzer show up again. We had Chandra, which observed X-rays. Compton has been defunct for a long time now. Chandra is still functioning, so there actually are two great observatories still working. Spitzer is defunct, but only for about a year. So it stuck around for a very, very long time. So these missions were all planned back in the 70s and 80s, and these things take a long time, but the good part is that they also last a long time. So that kind of leads us into Webb. So why Webb? So let's talk a little bit about why we need this telescope when we already have all these other ones in orbit, and why it's gathering infrared light, and how it came to be here. So as I said, I mean, each space telescope gives us access to a different part of the spectrum, a different kind of light. So, here are some objects, right? So on the top left, you have the Crab Nebula, which is the remains of an exploded star, a supernova. And Chandra, the X-ray telescope, observed this and was able to look at particles moving in that bright ring around it, and has been observing it for 20 years and watching it continue to expand from its initial explosion. On the top right is a star called Zeta Ophiuchi, which sounds a cool name. And Zeta Oph is a bright star, but it's mostly obscured by dust. All that stuff that you see in front of it, all those beautiful patterns are caused by dust. And Spitzer, if you remember, works in the infrared. So one advantage we'll see of the infrared, observing in the infrared, is that you can see through the dust. And so Spitzer was good for examining stuff like that. And then on the bottom, we have the Ring Nebula, which is the remains of a star like the sun will be 5 billion years from now, one thing that happens as stars like that die is that they puff out their outer layers into this big smoke ring. And the Ring Nebula is one of the prime examples. And then Hubble, of course, also gave us a lot of information about galaxies as well. And so those are the antenna galaxies. They are interacting galaxies. They're very close to one another, and they're gravitationally interacting with one another, and all that. All those bright dots are places where young stars are being born. So there's lots of action going on there. So those are all close to the Earth, but we can also look a lot farther away. So this image that's shown here is from Hubble, and this is the Hubble Ultra Deep Field taken in 2014. And there are about 10,000 galaxies in this field. There is, if I remember right, 2 stars in this field. Everything else in this picture is a galaxy. You can see the stars because they have the little diffraction spikes here and up in the corner. And everything else here is a galaxy. And this is basically a 25-day-long exposure with Hubble. So it's looking very, very deep. And as you may know, as we look deeper and deeper into space, we're really looking back in time because light takes a long time to travel to us. And so when we look at these galaxies that are far, far away, we're really getting a picture of what the universe was like billions of years ago. We'd like to know about the formation of the universe and the formation of galaxies and structure in the early universe. And to do that, we want to look farther and farther back. And that we'll see requires that we observe in the infrared. We can only see so far back using an instrument like Hubble, which works primarily at visible wavelengths. So Hubble observes mostly in the optical, very high image quality. You get these beautiful, beautiful pictures with really high resolution. Webb will do the same thing, only Webb will observe in infrared wavelengths. So it's going to really revolutionize our picture of the early universe, among other things. So why the infrared? Well, if we're talking about galaxies that formed in the early universe, sort of the first phase of galaxy formation in the universe, we're talking about a time period about 13 billion years ago. Now, and that's only a few hundred million years after the Big Bang. So the universe was very young back then. You have to, if you're not an astronomer, you have to get used to the fact that astronomers like to talk about, a few hundred million years as young. But the universe was young then compared to what it is now. And it was also much closer to the Big Bang. And the Big Bang led to expansion of the universe. And so the universe grows with time. And that has an effect on light that's emitted because light is a wave, or one way to think of light as a wave. And so if a wave is emitted in the past, as it travels through space and time, the universe expands and the wavelength of that wave expands. And what that means in practice is that if you emit a wave at short wavelengths, like the ultraviolet, which is short wavelength, as it travels farther and farther, it gets stretched into the infrared and then maybe even into radio wavelengths if we go far enough. And what that means is that as we look into the past, galaxies put out most of their light in the ultraviolet and visible wavelengths. And so if we look into the past, that light gets shifted into the infrared. And if we look far enough into the past, it's shifted so far into the infrared that it essentially becomes invisible to a telescope like Hubble. And we need a telescope that's sensitive to infrared wavelengths to really even see it at all. So I'll circle back to that in a little bit so you can digest it for a minute, and then we'll talk about it again. And maybe that'll help if it was a weird concept to hold on to. So let's talk about history a little bit. So this is actually an artist's conception from an early design of Webb, and you can see a lot of the features survived. If you remember when I showed you Hubble, I said it launched in 1990. And as I also said, these missions take a long time. So 1990 is 31 years ago. The first conference to start planning a successor to the Space Telescope, which astronomers aren't always very creative with naming, it was called the Next Generation Space Telescope, so NGST, which eventually turned into the JWST, the James Webb Space Telescope. And that happened, if you look at the cover of this book from back then, in 1989. So we started planning Webb before Hubble even launched. So here we are 32 years later, and people have had their entire careers go by as we've been planning and building James Webb. All right, so let's look at the telescope itself. So it has this really cool shape, right? I mean, it doesn't look like anything else. So let's talk a little bit about why it has that look and what all these pieces are, and a little bit about the technology that goes into it. So here's the mirror all unfolded before launch, and you can see it in the clean room on the lower right, suspended above its membranes of its sun shield. What do we have to do to make this telescope? Well, the mirror is made up of pieces, right? All these little hexagons that are really visible, not so visible here. You can sort of see maybe a little more visible over here, that fit together. And all of those pieces have to be aligned very precisely. And so one of the big issues with building something like Webb is that we want to be able to push the mirror segments around and move them when we're in space so that they form one consistent shape, right? The shape of the mirror that we want. We have to also do that with something that we can fold up, because Webb is too big to fly with when it's fully unfolded. The shuttle was able to carry the Hubble Space Telescope, but the Hubble Space Telescope is much smaller than Webb. And it was about the largest thing the shuttle could carry. We have the ability to carry slightly larger things than that into space now, but nothing the size of the Webb, so we have to unfold it. It has to fit into a payload fairing, the container that sits at the top of the rocket. That's only about 5 meters, about 16 feet or so across. And Webb itself, this mirror, is 6.5 meters across. So we have to do some folding to get it to fit in. So these 18 mirror segments have to be able to fold and then to be able to move around so that we can line them up. The whole telescope itself, what you see down here with the sun shield, all these membranes, is about the size of a tennis court. And it also has more than 100 little motors called actuators that can move it around and stretch it out and make it look the way it's supposed to look. So it all folds up as well, because you obviously can't fit something like that into a small fairing. So let's take a look at the mirror itself. So here's the comparison to Hubble. So Hubble's primary mirror is it's 2.4 meters across. That's about a little less than 8 feet. So if you're almost any room that you're in, it's about the same size from the floor to the ceiling. Whereas Webb is about the size of a 2-story building. So considerably larger, a little more than 6.5 meters, almost 22 feet across. You also probably noticed that unlike most mirrors that you see, I'll back up for a second since I didn't talk about it. Unlike most mirrors that you see, it looks gold, it doesn't look silver. And the reason for that is that, again, Webb works in the infrared. And the problem with silver and, to a lesser extent, aluminum, which is what we usually coat telescope mirrors with these days, those do not reflect infrared light very well. Silver in particular is black in the infrared, so it's not a good thing to coat your mirrors with. And it turns out the best reflector at infrared wavelengths is gold, and so these mirrors are actually coated with gold. It's not a lot of gold. The coating is only about 1,000 atoms thick, but nonetheless, they look gold because they are gold. The mirror itself behind the gold has to be stable at very, very low temperatures, because if we look in the infrared, we'll see objects that are warm look bright in the infrared. And so we want the telescope to be cold, because if the telescope is hot, then it only sees itself. You could imagine at visible wavelengths making a telescope that's made out of, light pipes or something wouldn't work very well. And so we need to cool the telescope. And so in this case, it's made of beryllium, which has the advantage of being relatively easy for us to cool, very strong, and very light. It's only about 2/3 the density of aluminum. So the telescope itself carries a bunch of science instruments. And for context, the picture in the background is the Virgo cluster of galaxies, which is basically the closest big cluster of galaxies. And again, most of the stuff in the frame that you see there is a galaxy, and some of them, look spectacular, and some of them look like fuzzy little dots, but they're all pretty much galaxies. And for scale in the sky, the whole picture here is about 2/3 the size of the moon. So these are packed fairly closely together. And all of those little squares and rectangles that you see there show how much of the sky is visible to these different instruments that Webb has. And they all have, astronomers love acronyms. And so they all have these acronym names, but the key thing to recognize in them is they all have IR in them, because they're all infrared instruments. And in fact, all but one have NIR because they're near infrared. So they're the part of the infrared that's relatively close to the visible, except for MIRI on the right there, which is the mid-infrared instrument. So, and what instrument you use depends on what kind of science that you use. Each is sensitive to a different kind of light. So the NIRSpec and NIRIS and NIRCam are all near infrared into just the reddest part of the visible spectrum. And then MIRI is longer wavelengths and basically good for observing cooler stuff. Now, NIRCam is just what it sounds like. It's a near infrared camera. And so it takes really high resolution pictures that look beautiful. But a lot of the science that's being done with Webb actually involves spectroscopy. So that's taking the light and stretching it out into its component colors. And I'll show you a couple of spectra later, not too many, so don't panic. But the advantage of doing that is it allows us to learn about things like the composition and the temperature and the density and the movement of the objects that we're looking at, something that you can't get from a photograph. And there's different kinds of spectrographs. There's the near infrared spectrograph. There's the near infrared imager and slitless spectrograph. So this takes a spectrum of everything that's in the field. That you can see at one time. This takes higher quality spectra, but only of one thing at a time. And then this takes spectra as well, but only at longer wavelengths, at longer infrared wavelengths. So I talk about spectra a lot, primarily because I'm a spectroscopist, and so it's near to my heart. But if you're not familiar with them, it's because they usually show up as graphs. And so when you read articles online or in the paper about Hubble, usually they prefer to show pictures than graphs. And so you're more likely to see something that looks like this than something that looks like that. But this is in fact what we usually look at. So we're taking the light where the instrument is spreading it out into its component colors, and that allows us to learn about these things like composition and temperature and movement of the objects that we're looking at. So here's the sort of cartoon version of it. And of course, there's two sides. There's the observing side of the telescope, kind of the business end, and then there's the side that faces the sun. We want it to be cold, remember, because hot things radiate, they're bright in the infrared. And so we want the telescope to be cold. And the whole purpose of all of this cool stuff here that's underneath is to keep the telescope cold. So that the sun hits this side, the underside here, this is what the backside looks like, and is reflected. And then we have multiple layers so that each one, some light, some heat gets through. And so we eventually, by stacking up all these 5 layers, we reflect so much light that the telescope is cold. So basically, if you think in let's do this in Fahrenheit terms, even though that makes me kind of cringe as a scientist, but the sun-facing side usually runs about 260 Fahrenheit. So, your oven when you're warming something up, right, and your leftovers. And without any kind of cooling at all, because this sun shield is so efficient at reflecting the sunlight, the innermost side is at minus 390. So there's a huge temperature difference across them. Most of the instruments are kept at about minus 390. MIRI needs things a little bit colder, so it has a kind of extra refrigerator on board to cool it a little bit more than that. But otherwise, the other instruments are just passively cooled. But that means that we always have to make sure that the backside here is the side that's facing the sun, right? You never want the sun to face hit the telescope side, or things would get really bad really fast. The other thing that happens on the backside is we have the solar array, which makes sense because it's facing the sun always, so that's nice. And we have the antenna, the little dish for communicating with the Earth. On the telescope side, we have the primary mirror. So so light comes in and bounces off this. It's bowl-shaped, so the light is reflected up to the second mirror, the secondary mirror, and then bounced back down through this hole in the middle. And then the instruments sit on the back side where it says science instruments here. There's no tube or anything because we don't, the purpose of a telescope tube on a small telescope is just to keep scattered light, stray light from other sources around. And when you build a telescope like this, there isn't any stray light around. It's just exposed to space. So we don't need a tube. Tubes are heavy anyway, so better not to have one. Now, when we launch it, it unfolds, right? It starts out as all packed up in a little ball, and then we unfold it after launch. It actually I'll show you the orbit in a minute, but it takes about a month after launch to get to the spot in space where it's going to spend the rest of its life. And during that month, it goes through all these phases. So on the way out to its final orbital location, it's going to unfold. It's going to unfold the sun shield, the 5-layer thing. You can see it spreading out. The little motors and actuators are then going to tension the sun shield because we want to stretch it so it's nice and tight. Then we unfold the secondary mirror, the support for it, this little tripod. We unfold the wings of the mirror. See, the mirror itself isn't round to start with because to fit it in the fairing, it's hinged and these pieces fold back. We unfold those and then it's fully unfolded. And then we're going to do some alignment by moving those little mirror segments around a tiny amount so that it looks to light that's coming in like it's one solid mirror instead of all these different segments. Deploying this whole process takes a month or so, but aligning it and commissioning it, making sure that everything is working, will take about another 5 months or so. So it'll probably be a couple of months after launch before we get our first image, and it'll probably be about 6 months after launch before it starts kind of routine science operations. It's in an interesting orbit, which is different from Hubble, right? Hubble is in a low Earth orbit, so Hubble orbits very close to the Earth. It's kind of like the lunar orbit here, only a lot closer. Webb sits way out here beyond the orbit of the moon. It's at a stable point called the L2 Lagrange point. And what that means is that if I put a satellite, put something exactly at the Lagrange point, it would stay there, more or less. If I put it close to the Lagrange point, then it orbits it. So it's going to make little circles around here. And the nice thing about that is that it's always got the same orientation with respect to the Earth and the sun. And so it's always got the dark side, the reflective side facing the sun. So this is good. The disadvantage, of course, is that it's not serviceable like Hubble is, right? Hubble, we could go up and we could change instruments and we could make repairs and so on. This is way too far away for us to do that. I think about 1 million miles or so from the Earth. So once it's there, it's there, which causes sometimes a little bit of concern, right? What if something goes wrong? But, we've done this before, right? So the Kepler Space Telescope was far away from the Earth. The Spitzer Space Telescope, the infrared great observatory that just died a year or so ago, is also operated for many, many years, and was also in an orbit where we couldn't actually reach it. The nominal mission for Webb is 5 years. That would be considered a success, but it has enough fuel on board for 10 or so years of operations. It needs fuel because as it orbits around, it drifts a little bit, and so it's got not very much fuel. You could carry it. It's only about 20 or 30 pounds of fuel, but enough to kind of make little corrections while it's out there and make sure it stays stable. And actually, fueling of the telescope was just completed, I think, the day before yesterday. So we really are ready to go. While it's out there, we talk to it. The telescope is operated from the Space Telescope Science Institute, which is in Baltimore, which is the same place that operates the Hubble. The one nice thing about where it's sitting, Hubble, of course, orbits the Earth. It goes around and around, and so its location from the ground is always changing. So it's a little more complicated to communicate with. Webb will sit out there in a much more stable place, and so it's easier to communicate with, and that allows us to use the telescopes of the Deep Space Network out in California, which are these big dishes, to talk to the telescope. And that's important because the amount of data that goes back and forth is very, very large, mostly comes down, and larger than with Hubble. And so having the big dish be able to talk directly to the telescope all the time is a huge help in that regard. Okay, so one other thing I wanted to mention, I mentioned earlier that the Europeans are involved in Webb. I mean, it is a NASA-led mission, but the Europeans have a chunk of it. And in fact, you can sort of, all the dots on here are the locations of either universities or companies that were involved in building the telescope. So you can see it really is an international effort, even if it's led by the United States. So it's 14 countries, I think, so lots of people involved in it. All right, so let's talk about the infrared a little bit more. So we can build telescopes to work at all kinds of wavelengths. I mean, visible is perhaps the easiest for us, but we can build telescopes to work at gamma ray wavelengths, like I showed you before, and we can certainly build telescopes to work in the infrared. And so that's the part of the visible, or the part of the optical spectrum that's just longward of visible light. So the wavelengths of light are a little bit longer than visible. So why does that help us? Well, here's a picture of a somewhat Floridian-like animal on the right and a considerably less Floridian animal on the left. And these pictures are in visible light. And so this is kind of what you're used to seeing, right? And so what we're really seeing here is light reflected from these objects. But when we look in the infrared, they look very different from that. So the meerkats are glowing, and they're glowing because they're mammals. They have a high body temperature, and objects that are warm put out infrared light. They emit infrared light. It's not reflecting light here. It's actually generating it. It's just that wavelengths that our eye can't see, but of course, something like Webb can. And on the right, we have the saltwater croc. And here, he's just come out of the warm pool that was here. So he's still kind of warm, but you can tell he's nowhere near as warm as the warm-blooded animals are. So here's the full infrared spectrum. It goes all the way from gamma radiation through X-rays to ultraviolet to visible, infrared, and then microwave and radio. So this whole range of stuff. These are all light. They're just different forms of light. Our eyes are only sensible to visible, which we think of as being very complex, and there are all these colors and everything. And it's true, but it's still a tiny, tiny piece of the full visible spectrum. So Hubble is sensitive to visible light, but also to somewhat in the infrared. And Spitzer was sensitive to light wavelengths that were considerably longer in the infrared, and Webb kind of overlaps Spitzer, but mostly fills the piece in the middle. They're kind of to scale here. Certainly compared to Spitzer, you get a sense of how much bigger Webb is compared to Spitzer. A big advantage of working in the infrared is that we can see through dust. And that matters a lot because a lot of things that we're interested in are shrouded in dust. So here's the sort of pillars of creation, this famous image from the Hubble Space Telescope. And these are all stars that are forming, but the stars are all behind this dust. You can see them lighting it up here and in some other areas like here. But generally, you can't see the stars themselves that are because they're shrouded in this dust that they're going to form out of. There are these giant clouds of molecules and dust that the stars form out of. The stars that you see here are actually between us and the pillars, and so they're unrelated. But if you go to the near infrared, where Webb operates mostly, suddenly it becomes a lot more transparent, and you can actually start to see what's going on inside. And if you look in the mid infrared, where the Mira instrument works, now you can actually see the dust glowing. I mean, the dust is glowing because it's quote unquote warm. It's not that warm, right? It's only probably about 100 degrees above absolute zero, but that means it still emits light in the mid-infrared, and so now you can see the dust itself. So it allows us to see the dust itself and what the dust is hiding from us, and we can't do that without working in the infrared. So this is one big advantage of Webb. The other big advantage of Webb is that it's large. Astronomers like big telescopes. We larger the better, and we colloquially call them light buckets because their primary purpose is just to collect lots of light. Webb is 6.5 meters across compared to Hubble's 2.4 or 2.5, so it's collecting a lot more light. The other thing that being larger gives you is better spatial resolution, better resolution. You can see more clearly. Your images are sharper. And so Webb will both see fainter objects and see them more sharply than we could see with Hubble. All right, so let's look at a little science that we have in store with Webb. So one thing we can do is look at the early universe. So this is what I talked about a little bit before. So we want to see back as far as we can toward the Big Bang, which is around 13.5 billion years ago. And during that time, which is called the era of reionization, the universe became transparent. If you go back too far, the universe is opaque and we can't see through it at all. But when the universe becomes transparent, we start being able to see the early galaxies that form. And remember, they are emitting their light almost all in the ultraviolet. But since the universe was so much smaller back then, that light wavelength expands as it moves towards us or moves into the future. And by the time it reaches us, it's not ultraviolet light anymore, it's infrared light. The problem with Hubble is that if we want to see galaxies back from when the universe was young, back from the first era of galaxy formation, the light that they're emitting has been shifted to colors in the spectrum that are so red that Hubble can't even see them anymore. Here's what a Hubble image of a really young galaxy looks like. It doesn't look very exciting. But one of the interesting things, in fact, about these early galaxies is that if we look nearby, which means in the current universe, we see all these beautiful patterns, spiral galaxies and barred spiral galaxies and the like. And as we go back into the past, galaxies don't have that kind of structure. They become much more irregular and much dustier. And so you don't have this beautiful spiral shape. But when we look at this with Webb, we should be able to see considerably better. We'll have better resolution, we'll have a brighter image, and we'll be able to see more. Now, here's a kind of flip book of galaxies that Hubble put together. So this goes through time. So the one on the left here is in the local universe. It's nearby, which to people who study galaxies, nearby means like it's only 10 million or 20 or million or 30 million light years away. So it's, it's basically out by the post box. But as you go back here into these, you're going back into the past, and you'll notice what I just talked about, that you have this nice spiral here, and here you have some cool kind of structure. And as you get farther back, they get more and more blob-like until you get here. And notice it's also they're getting smaller and smaller, and they're getting harder and harder to see. And if we were to try to make the next step here with Hubble, we wouldn't see anything at all, because all of the light, or most of the light, has been shifted to wavelengths that Hubble isn't sensitive to. But we want to be able to see that. And so we're going to take advantage of Webb's ability to see in the infrared, to look at these galaxies that formed when the universe was young. We're going to be able to look at black holes, not the hole itself, but the material surrounding it. So our galaxy, the Milky Way, has a central supermassive black hole, Sagittarius A star. I tell you, astronomers are not very exciting and creative about naming stuff. But Sagittarius A star is hard for us to see because it's shrouded by dust. There's lots of dust toward the core of our galaxy. And what is Webb good at? Well, Webb's really good at looking through dust. And so we will be able to look at the environment of the black hole at the center of our galaxy. And we'll also be able to do the same thing with neighboring galaxies, with nearby galaxies. So quasars, which you may have heard of, are some of the more powerful and exciting objects in the universe. And they are supermassive black holes that are eating, basically. There's material spiraling into them. And as that happens, here's the artist's conception, right? This is not a picture. As material forms a disk and spirals into the hole, it heats up. So it puts out a lot of light. It forms these jets of material that shoot outwards. All of this is typically shrouded by lots of dust. And so if we want to see the structure close to the black hole and figure out what's going on, and understand how these central black holes help shape the galaxy that they're in, we need to be able to look in the infrared. And so Webb will do that, and it'll look at how quasars were behaved in the early universe when they were much more common than they are now. We'll also look at stars. This is kind of like the image that you saw before, right? So we look in the infrared and we're able to see through the dust. And this allows us to start understanding more about star formation, about how stars form, where stars form, what that process is, because we can look through the dust and see what's happening inside it. It also allows us to see in these star forming regions molecules, because these clouds have gas and dust, and a lot of the gas is in the form of molecules, usually not very complicated molecules, things like carbon monoxide and carbon dioxide and ammonia and things like that. But there are also some more complicated molecular clouds. There was a famous paper someone had fun with 20 or 30 years ago where they calculated how many bottles of vodka equivalent there were, because they discovered the cloud had alcohol, was alcohol molecules. But we're going to be able to use Webb to look at stars in different kind of environments and see how the kinds of stars that form depend on the environment. Are we forming stars that are like the sun, or for stars that are much less massive than the sun, or the really high mass stars that are exciting but live very short lives? So we're going to look at these star formation regions. So I started far away and I'm getting closer. Hubble has taken spectacular images and spectacular spectra of objects in our galaxy, and Webb will do the same thing. So here's an image of Jupiter, which probably doesn't look like most images of Jupiter you've seen. This is a Hubble image, but it's in the infrared. And so this is the kind of image that Webb will do. And that will allow us to do things like understand the atmosphere of Mars and map the cloud structures on the gas giants like Jupiter and Saturn, and study seasonal weather and climate on both the gas giants and their moons, as well as seeing objects in the far outer reaches of our solar system, so asteroids and objects in the Kuiper belt, out beyond Pluto. Because again, it can collect a lot of light. Those objects radiate light, but they radiate light in the infrared because they're very, very cold. So one of the things that I study is distant planets. So not planets in our solar system, but planets in other solar systems. So this is, I love this image. This is from a ground-based telescope, the Keck telescope in Hawaii. So obviously this is a sequence of images taken over time. And this is a star. It doesn't have a name. It has a catalog number, HR 8799. The star is actually where the little star is. This is taken with an instrument called a coronagraph. So it blocks out the light from the star so we can just see the stuff around it. It's really hard to do that, which is why there's this weird flickering in the middle there, because the process isn't perfect. But you can see these 4 little dots, and over time they move, and those are planets. And they're planets that are orbiting the star, and we've been observing it for long enough that you can actually see them make little arcs in their orbits. And I think this is like one of the most amazing things ever. It just looks so cool. The reason the planets are glowing is that they are young. They have just formed, and that means they're hot, and hot objects radiate in the infrared. And so Webb will be really nice for looking at these young planets as they form. Now, if you're not interested, so these are mostly gas giants, so they're Jupiters or bigger than Jupiter, but maybe you're interested in more terrestrial-like planets, and a lot of us are. And one of the reasons you might be interested in them is, habitability, right? We all want to know, can they have life? And one of the things that we require for having life is an atmosphere. And so we want to look at these planets and discover whether they have atmospheres and what those atmospheres are made of. And if you remember, I said we could use TESS as a finder telescope. So we're going to find a nice potential planet that might be somewhat Earth-like, that's transiting, that's moving in front of the star. And then we're going to be clever, because when the planet moves in front of the star, I told you it blocks the light from the star. But if it has an atmosphere, it blocks the light better at some wavelengths than others, because the atmosphere absorbs some colors of light and not other colors of light. And so if we're really clever, we can compare how much is absorbed at different wavelengths. And from that, we can figure out whether there's an atmosphere and what that atmosphere is made of. Now, we're trying to do that now, but it's really hard because it's a very, very, very weak signal. So here are some modern, really good efforts. So the top one is from Hubble. And let me explain for a second here what we're looking at. So this is a spectrum, right? It's just a graph. So it's how bright the thing is, the planet, as a function of wavelength. So this goes from the ultraviolet to the near infrared. And the solid line and all the stuff around it is a model. It's someone's idea of what the atmosphere looks like. And then all these little dots with the error bars on them are the measurements. And you can see this is really hard, right? There are not many dots and they have huge errors associated with them. But we still think we see this peak here, and this probably due to sodium. but out here, clearly we don't have any idea what's going on, right? Because it doesn't match well. This is, the bottom one is the same thing, but this is from the ground using the VLT. This is the largest, or one of the largest ground-based telescopes. It's a European telescope in Chile. They're just as creative as every other astronomer. So VLT is the very large telescope. And so here are all the VLT measurements, and you can see, I mean, here, you know, again, you see sodium, but you also see maybe peaks from other things. But, you know, I wouldn't consider this the most convincing thing. So what do we expect to see when we look at a planet like this with James Webb? Well, the answer is something that looks like this instead. Now, there's lots of lines here, but just ignore most of them except here. And this is kind of what you expect to see with Webb. And now you can identify these peaks with all kinds of things: carbon monoxide, water, ammonia, methane, all sorts of good stuff. And we're out in the infrared now. Now, the previous one went all the way out to just 1 micron, right? The visible wavelengths are right in the middle here. And this starts almost at 1 micron and goes all the way out to 5 microns, which is well into the infrared. And you can see the little labels on the bottom here tell you which James Webb instrument we would use to look at those pieces. So we'd observe with several instruments and piece it all together, but this would allow us to kind of figure out what's in these, whether these planets have atmospheres and what's in them. And the planets that TESS detects are the ones that are going to be good for this. And so they really are, they work well together, TESS and James Webb. All right, so where are we at? Webb is being launched. One of the contributions the Europeans are making to Webb is they are launching it. They're providing the launch vehicle and the ride to space. I don't know if you followed in the news. You know, there was a whole thing about, oh, we have to not tell anyone when we're sending it because of pirates, et cetera. But it did go on a ship and travel through the Panama Canal and ended up in Guyana. It's being launched on an Ariane 5, which is the largest. So Ariane is the European big rocket manufacturer, and Ariane 5 is their biggest rocket. And so you can sort of see it in here, folded up inside the fairing. So it's going to sit on top, and here it is all folded into pieces. And then if everything goes well, you know, in just a few weeks, we will get launched into space. The picture is not really representative since we're supposed to launch at 7 in the morning, but I'm kind of chasing a moving target here. But that is an Ariane 5 launch, so that's kind of what it will look like. So we're all excited and terrified at the same time. It's eaten a lot of astronomers' time and a lot of astronomical budget over 30 years, and this is going to be kind of all our eggs in one basket when it launches. So a lot of astronomers will be kind of doing the horror movie look at the launch when it goes off, but exciting for sure. And then we look forward to you know, at least a decade of astronomical discovery with this wonderful space telescope. All right, so I think I can stop. So if you have questions, I will try to answer them.
Had a variety of questions. I know Kelsey has some as well. I'm going to scroll all the way to the top really quick. One question was, aren't antennae galaxies like irregular galaxies?
They are, because of the interaction. So,
okay.
I mean, when galaxies interact, it's not like the stars all collide with each other. I mean, they can sort of pass through one another, but the stars and the gas and dust clouds interact gravitationally with each other. And so usually what happens when galaxies interact like that is it triggers a lot of star formation because the clouds start getting stirred around and compressed. And so you get this big burst of star formation, and they have lots of massive, young, bright stars radiating lots of ultraviolet light. And they're called the antennas because after they pass through each other, they leave these long tails where material gets pulled out. There's another pair called the mice for similar reasons.
One question is the Deep Space Network. How does the images kind of get communicated back to Earth, or is the Webb telescope able to communicate directly to us?
It does communicate directly to us, but through DSN, through the Deep Space Network. So, I mean, they come back as bits, right? So it's just computer signals, ones and zeros that come back, and then they get converted back to images and spectra on the ground. I mean, two kinds of data really come back, really. So there's the science data, the data from the science entrance, and then there's housekeeping data. So we keep track of where's the telescope pointed, what is the temperature of the telescope, all those kinds of things that we want to know about, and keep track of everything being healthy.
The Hubble was expected to only operate 10 years, but it's going on 31, correct?
Correct.
And do we
So,
think
I mean,
that,
well, Hubble, I mean, we could extend Hubble's life with servicing missions as well, right? So that was an advantage. I mean, if the question is sort of leading up to might Webb last a lot longer than 10 years, I mean, yeah, I would say it's certainly possible. I mean, the engineers tend to get ridiculously clever at figuring out ways to extend the spacecraft. And you learn as things go, right? I mean, the 10-year lifetime is based on what we think it's going to take to do all those little station keeping moves and when we'll run out of fuel. But as you do it, you get better at it. You learn how to do things using less, and the engineers will be doing that all the way through. And so my guess would be that if everything keeps working, then it probably will last longer than 10 years.
and for I can't remember the full name of the star, the Sagittarius one. Are
Sagittarius
A
A.
star.
Sagittarius A, are we studying the unusual flares emitted by the Sagittarius A?
Well, I don't know how unusual they are, but we certainly are studying, radiation from the system. Yeah, I mean, it does emit light and all kinds of wavelengths, including we've seen a 511 keV line from there, which is due to electrons and positrons, which are the antiparticle to electrons annihilating each other. So that's kind of exciting that there was antimatter present as well. But certainly it emits gamma radiation, it emits X-ray radiation, and so on. So it's all kinds of stuff. Another cool thing about the central black hole in our galaxy is there's this beautiful study made over decades where they were able to figure out the mass of the central black hole by looking at stars nearby and how they orbited it. So Kepler's laws let you, translate if you know how big the orbit is and you know how long it takes, you can figure out how massive the thing is in the middle. And these stars move incredibly fast because the central black hole is, I don't remember, but on the order of 10 million solar masses. So it's.
We did have a related question to black holes on, are black holes even black, or how did they get their name?
Well, they get their name because just sort of first order things go in, but they don't come out, and black hole, and that includes light. And so black holes don't really radiate anything. And so, they're called black holes for that reason, that they don't emit light. That's not exactly true. I mean, there's always provisos to everything, but the amount of light that they emit is very, very, very small. And so black hole is a perfectly good name for them.
And did your work contribute to finding the first exoplanet?
No, unfortunately. I did contribute to the picture behind me is Kepler 16b, which was the first planet found around a binary star, and I did contribute to that work.
Very cool.
What happens to the rocket?
So I mean, Ariane is an expendable, and so you're a little outside my comfort zone, so I'm not entirely sure.
We're not sure.
I think they'll I think the boosters will get recovered. I'm not sure about the main rocket body at all, whether it is lost or whether they actually recover. I mean, it'll come back to Earth for sure, but whether it's recoverable, I don't know.
And we have a question. Do you know for sure that the telescope will stay on its track? That's a great question.
You mean once it's in orbit? I mean, yeah, it's celestial dynamics, and over the last 100 years, we've gotten really good at that. So that part I don't have any issues with. If it doesn't, it'll be because of some mechanical failure, not because of a lack of knowledge or ability on our part. But we've gotten really good at it, and we've gotten very reliable in space too. So I have the most dangerous part in the sense of risk is probably the launch, right? Once it's up, my worries get a lot less.
Okay, so one question was whether the Webb telescope has been released yet, and it has not been released just yet. So the launch date is the 22nd of December.
So just
do we
about
know
2 weeks, yeah.
Yeah, so,
Very-
so it's-
It's expected to launch December 22nd, 2021 at 7:20 in the morning Eastern Standard Time or 6:20 Central Standard Time.
and do we know how long it kind of takes for the launch to kind of get to its desired location?
Well, it'll get into low Earth orbit pretty quickly. So, I mean, that's a matter of, tens of minutes. But then it has to move out to this location, this L2 location. That will take about a month.
Okay.
We're not in any rush. There's no reason to do it fast. And we're going to unfold the telescope in very careful stage managed stages. And so a month gives us time to do that as well.
So it'll take about a month for it to travel 1 million miles, if I understand correctly.
Yeah, that's about right.
That still blows my mind.
And will the Webb telescope be able to see other planets or galaxies?
Yes, yes to both. Yeah, it will see other planets around other stars. Yes. I mean, it's not going to see them in the sense of, making pictures where you can see continents or anything. It's going to be, you'll see dots of light, but it will be able to detect some planets around other stars. And it will certainly detect many, many, many galaxies.
And other planets outside of our solar system are called exoplanets, meaning they're external to our solar system. So exoplanet.
It used to be, when the field was really young, some people called them exoplanets and some people called them extrasolar planets. And over time, the exoplanet usage has won. But I have old papers that call them extrasolar planets. So it's just what people are comfortable with. And now everyone calls them exoplanets.
There's a question, why is Jupiter's great red spot shrinking? Do you know that one?
I do not know the answer to that. I mean, I'm not sure anyone knows the answer to it in detail. I mean, in general, I mean, it's a cyclonic disturbance. So you could sort of think of it as something like a hurricane. And on the Earth, those have limited lifetime. So it's not shocking that it should have a limited lifetime. It's just hundreds of years instead of, a week or a couple of weeks. But the speeds and the amount of energy involved are much, much greater, of course. I mean, the Great Red Spot is several times the size of the Earth.
Would the Webb telescope look at the central core of black holes in the Andromeda galaxy?
I mean, they'll certainly use it to look at the supermassive black hole in Andromeda. How close they can get. I mean, they won't see the hole itself. Anything they see will be associated with the disk of material around it. I don't know how close to the center they'll be able to get. I'm sorry, it's not really my area, and so I have to speculate a little bit.
And we're very interested in black holes, so we're curious what's inside.
Yeah, I mean, it's sort of an unanswerable question, right? I mean, because how do you know? Well, you go in, I mean, that's how we find out anything, right? You go there and you find out. Well, or you look at the light that's coming from something, and you use spectroscopy or other tools to interpret it. And the problem here is that, light doesn't come out of a black hole. So that whole raft of tools isn't available to you. And, you can go in and you can say you're going to go in and look, but there's, problem one is that you can go in, but you're not going to come back out. And problem two is that you're going to be ripped apart and turned into half into X-rays on the way in. So you're not going to be in any shape to tell us anyway. So, I mean, all I can say about what's inside the black hole really is that it's matter. Beyond that, it's difficult to say.
But you can study the size and how the black hole rotates. That's
right.
You can continuation on the
black holes can, they can rotate. They can have electric charge. But their most prominent characteristic is they have mass. And just since we're talking about black holes, people always worry about being sucked in by a black hole or something. But if you're not close to the black hole, it acts like any other massive object. So I mean, if I replace the sun with a black hole right now, I mean, the black hole would be a lot smaller than the sun, but the Earth's orbit wouldn't change. We'd still keep going around it. It just would be very dark and cold for us.
I'll let Kelsey do the staff question.
Right, Kelsey.
Which one are we at? From
Your staff question.
Your staff question.
Oh, she was asking why is Webb launching from French Guiana, another country? And the entire reason is because when you're launching so close to the equator, it helps kind of serves like an extra oomph or push to get the rockets into orbit or to leave our atmosphere.
Right. So, if you're close to the Earth rotates with a speed of something like 1,000 miles an hour when you're close to the equator. And when you get far from the equator, that speed is a lot less. And if you launch in the same direction as the Earth's rotation, you get that extra little kick, which allows you to launch either, heavier stuff for the same amount of fuel or, things that you couldn't launch at all. And Webb is big, so we want to take advantage of that. And the reason, of course, it's launching from another country is that part of the European contribution to the mission is the launch. They've also contributed to at least one of the instruments.
And we have several more questions. So I'm just going to kind of read them in order. We have another black hole question. What about the core black holes in the Virgo 1 system? Do you think that the Webb will be able to see those?
I don't know. My guess would be yeah, because Virgo is not that far away, and so yeah, I would think.
Andromeda is also in there, so.
Well, Andromeda is a lot closer. The Virgo cluster is considerably farther, but still,
Yeah.
I don't. The level of detail I don't know, but it certainly should be able to see central black holes in Virgo.
And why was Jupiter's red spot not bright red on the infrared camera?
Well, because invisible light, it's red because of reflection. And so it's whatever, in the case of the great red spot, it's whatever organic molecules. And I'm not going to be able to recite what they are to you because I don't remember. But, it's whatever organic molecules are present there that happen to reflect a lot of red light. And so it looks really red. But in infrared wavelengths, it's completely different. Now we're not seeing the reflected light, we're seeing the heat. And the spot is kind of like just like a hurricane is kind of like a hole, right? If you look at the core of the hurricane, you can, imagine looking at a hurricane from space. When you're not looking at the center, you see the cloud tops, but then when you get close to the center, you see much deeper. And the same thing happens with the spot. And so when we're looking in the center of the spot, we're seeing deeper into Jupiter, and Jupiter gets hotter as you go inside. So it's going to get brighter in the middle of the spot. So now you're seeing temperature differences instead of color differences.
We have a lot of great questions from Girls Inc. How will the Webb telescope be protected in space?
It doesn't really need a lot of protection in space. There'll be some micrometeorite impacts, but it's so large that the occasional tiny little hole here and there isn't going to matter. The only other thing I would worry about protecting it from is solar radiation, right, which can be hard on things, but it's got this beautiful 5-layer sun shield to protect it from that. So I think that's probably more than enough. If we're putting it up there for 100 years, I might worry a little bit more, but for 10 or 15 years, I'm not especially worried about it.
And why is Pluto no longer a planet, but a dwarf planet?
You must get that a lot.
I'm laughing because so Pluto was discovered by Percival Lowell, which is one of the reasons it has its name, because he not only named it after the god, but his initials. Well, he didn't discover it, but the observatory that it was discovered from was his observatory. And a friend of mine from actually high school and graduate school is now the director of that observatory. So he, of course, rolls his eyes every time this comes up because their Lowell Observatory is never going to say that Pluto is not a planet anymore, no matter what anyone else says. It's very, it's controversial. There are, the people who decided this came up with criteria for what makes a planet, and some of them are sort of relatively simple stuff, like it should be round, and that just means it's big, right? Because if something is really small, it can have any shape, but as it gets bigger, its gravity, as it pulls on itself, forms it into a ball, and so that little things like small asteroids are not planets, but the biggest asteroids like Ceres actually are round. They're big enough to be planets. And so the line is a little bit arbitrary. So, what they would say is it should orbit the sun for a planet in our solar system. It should be round. And the last one is the tricky one because it's supposed to have cleared its orbit, which just means that it's swept up or ejected all the other stuff that might be around. So that means like Ceres, the biggest asteroid, is not a planet because there are all these other asteroids around, right? I mean, it's just the biggest one of this big group. It hasn't cleared all the other ones out, whereas the Earth has, and Jupiter certainly has. Pluto, the argument goes, has not cleared out its orbit. It's a little bit unfair because it takes longer the farther out you are. So, Pluto, even if it was able to clear its orbit, it couldn't have done it in the time that the solar system has been around. So it's a little bit unfair as a selection criterion, but that's it. I mean, it's kind of, in a way, it's kind of silly because, I mean, if you saw how it happened, I mean, a bunch of astronomers at the International Astronomical Union voted on this proposal about whether Pluto should be a planet anymore. And I mean, doesn't seem like, one, something you should vote on, and two, 90% of the astronomers voting were not planetary astronomers. And so, my opinion on whether Pluto should be a planet or not is worth almost nothing because it's not what I study, right? I mean, someone who actually works on in that area, their opinion should be worth a lot more than mine is. People still argue about it.
We received a thank you. Our family saw a model of the Webb telescope at Goddard Space Center, and it was wonderful learning more about it. How do you see the Webb telescope in space? So how will we be able to, I guess, keep an eye on it? Are we able to see it when it's up there?
How bright it's going to be because it's pretty far away. I don't think it'll be a naked eye object, but if you had a small telescope and you knew where to look, I think it would be visible.
And what is inside a telescope?
Yeah, so I mean, here let's see if I can run back here. I mean, telescopes are really quite simple, right? So it really is. I mean, you're really seeing everything except the instruments here. So, I mean, it really is just a big mirror that is somewhat bowl-shaped, which takes the light coming in and sends it up here. We've got our secondary mirror, which reflects it back down, and then we have the instruments that sit back behind the primary mirror. And kind of what you see is what you've got. I mean, it's not complicated. The complexity, there's complexity in the instruments, but the telescope itself is a relatively simple thing, except for the fact that we need to adjust these mirror segments and all this other stuff. So that's kind of where the technology is. So the complication is the precision with which it's made and moved more than, the complexity of design.
There was a question, why couldn't we launch the Webb from Hawaii or Florida? I think that's our last question.
Well, I mean, Hawaii, we don't really have we don't have the ability to launch big things from Hawaii. I mean, it's difficult to get to, and you'd have to move everything out to Hawaii, right? Not just the telescope itself or the satellite itself, but also all the launch equipment, and there's no facility on Hawaii for launching things. I suppose we could have launched it from Florida. I mean, I don't know the politics of how that worked out exactly. I'm not in tune enough with how it was decided that would be the European contribution that would be the launch. I mean, it would have been hard anyway, because I mean, the telescope was built in California, and so you've got to move it from California to Florida, and that's not a trivial thing either. I mean, you maybe could think about trucking it, but it's a little big for that. And so, I think you'd end up putting it on a ship anyway, and then it would have to come around through the canal. And it's even a farther trip to Florida than it is to the northern coast of South America. So, 6 of one, half dozen of the other there. But I think the Europeans had a really strong case for their launch because, we don't have, I mean, shuttle's not available anymore. Ariane 5 has an excellent track record and is capable of launching, really big payloads. And the Europeans have done this a bunch of times before, so it was a good match, I think. And it was a good way for them to provide. I mean, I don't remember exactly what their share is of the telescope. I think for Hubble it was like 15% or something like that. So I'm guessing it's around the same for Webb. And a launch and an instrument and the associated support comes to roughly that. So that's pretty reasonable.
And right now we're just receiving a lot of thank yous, and thank you for the presentation. I really enjoyed learning more about the James Webb Telescope. Thank you for this wonderful program.
Oh, thank you.
Is there anything else you'd like to add?
I'm good. I noticed looking at this, I didn't talk about the star trackers, so
Okay.
I'll name them for a second. So these are just little telescopes, basically, that look at stars to help orient the main telescope. So when Webb is slewing around and pointing at different pieces of the sky, it needs to know where it's looking, and so the star trackers look out in not the same direction as the telescope, but they're multiple star trackers looking in different directions, and they look at the field of stars that they're pointed at, and they can then figure out where the telescope is pointed. So they are important.
I think that is it for the questions. So
Thank you, everyone.